Hi guys, we were discussing about this current electricity. So in the previous class, we learned about what is current. Current is nothing but the rate of flow of charge we define as electric current. The rate of flow of charge. This units we can take coulomb second inverse that we define as amperes. Now after that, current is a scalar quantity because it do not follow the law of vector addition. So to know the relation about voltage versus current, or precisely if you can say potential difference versus current. So we have talked about Ohm's law. Ohm's law gives a relation between potential difference is directly proportional to current for a given conductor. For a given conductor, the potential difference is directly proportional to current. So potential difference V is directly proportional to I. So we will remove proportionality constant. We introduce a new character or new property for conducting materials or any kind of materials. So that new property is nothing but resistance. So from this we define resistance R equal to V upon I. So here R we define as resistance. So R is nothing but resistance. Now this resistance is material property. So different materials possess different resistance values. So if we can take the resistance units, so resistance we are representing as ohms. So if you can define 1 ohm equal to 1 volt upon 1 ampere. So this is unit of resistance. Now the factors which are affecting the resistance. Factors affecting the resistance. So from the experimental verification, we'll come to know that the resistance is directly proportional to length of the conductor and the resistance is inversely proportional to area of the conductor. So this together we can write that the resistance is directly proportional to L upon A. Now we can remove the proportionality constant, we can replace another constant. So that's known as rho, which is also known as resistivity. So resistance, another formula in terms, not in terms of voltage and current, in terms of the length and area of cross section and resistivity. Yeah, this is termed as rho, and this is also known as resistivity or specific resistance. So from here we define specific resistance, a rho equal to R times A upon L. If you can write the area in terms of length into, just like write length into breadth or length into length. So if you can write that area as length into breadth upon L, so length gets cancelled. The resistivity rho equal to R times B. Here the breadth is in terms of meters. So R times B here, don't be confused with the new character what is B. So here I can write that So that is one of the dimension. So finally, I can write resistivity rho equal to ohm meter. So resistance units are ohms, and the B is I consider as an abroad since it's having area. So ohm meter. So this we can define as specific resistance or resistivity. It is defined as the resistance of a conductor of that material having unit length and unit cross section area of cross section. So if we can define the resistivity, how we can define the resistivity? If we can take that specific resistance of a material, it may be defined as the resistance of a conductor of that material having unit length and unit cross section area. So this we define as a SI unit known as specific resistance. So this units we can write in terms of ohm meter. So here I am having certain table. So if we can look into the table, so before that looking to the table, I will make you to know if you can take the conductors and the electrical character. So we know the best conductor that copper, iron, silver, aluminium and nickel. So these are the metals. And first we can see this property of electrical resistivity. So the electric resistivity having very less. So it is the resistance per centimeter. So the copper value and as an silver and as an aluminium and nickel. So these material having as an electric resistance which is very low, and we can define that material whether it is good for electric purpose or not by two characters. If it is a conductor, it should have high conductivity. So conductivity and resistivity are reciprocal. So here if I can define conductance, if I define conductance as first, the reciprocal of resistance is known as conductance. So we can represent that as conductance G, conductance. So this is another term. Conductance we can use represent the capital G. So conductance equal to the reciprocal of resistance, or G equal to 1 over R. So R units are ohms, it means 1 over ohm. So therefore G units are ohm inverse. So this is the new definition at here, conductance. Conductance we define as the reciprocal of resistance. So its units ohm inverse, or this is also known as G units, also known as Siemens. So Siemens are the units of conductance. So if you can give as a comparative study for the resistance and the conductance, so that will be helpful to for the better understanding. So whenever you can study the conductance or first resistance, so resistance rho R equal to V upon I, or resistance R equal to rho times L by A. So this is the resistance 2 formulas. Till now so far we learned. Similarly, the reciprocal of resistance is known as conductance. This G we are representing as conductance. And resistance units are ohms and conductance units are ohm inverse. Likely here we define resistivity. Resistivity is nothing but a rho. So the similar term for conductance, so we can define that as conductivity. So we can define conductivity as the reciprocal of resistivity. The reciprocal of resistivity we define as conductivity. So conductivity equal to 1 over resistivity. So in symbolic form we can represent that conductivity we are representing sigma, sigma equal to 1 over rho. So if we can take units, 1 over rho units are nothing but ohm meter resistivity. So it becomes ohm meters. If you can take to the numerator ohm meter inverse. So it's supposed to be whole inverse. So far, these four definitions, conductance and resistance, or resistance and conductance. R is resistance. If we can do reciprocal of R, that we can give the conductance. And rho is resistivity. If we can do the reciprocal of rho, we can get sigma, that is known as conductivity. So let me explain now this table which I am having, conductivity versus resistivity. Now resistivity, if you can take that as rho, and conductivity you can take that as sigma. This is sigma. And conductivity, resistivity, they always go reciprocal because sigma equal to 1 over rho. If the conductivity is more, then the resistivity is less. So in the same material, they both go inversely proportional. So that's the reason if you can take copper, so the copper is a good conductor, we know that. So the copper is good conductor. Here is copper. You can see the conductivity of copper, it's a huge 29 times 10 power 5 ohm meter, ohm centimeters inverse. And if that much is the conductivity, now if you can see the resistivity, it's having very less resistance. It's the order of 0.034 times 10 power minus 5 ohm centimeter. And if you can see the next one, below the next one, iron. Now iron is having high electrical resistivity. It's having high electrical resistivity. Now if you can see, it's the conductance. If electrical resistivity is more, obviously the conductance is less. Now its conductance value is very less because it's having high resistivity. Similarly, when you can see the below the next one, silver. Silver is a good conductor. So if it's a good conductor, it should have resistance less. It's having resistance very less. And when it comes to conductance, it is having good conductance, 2.8 times 10 power 5 ohm centimeters inverse. So that's why for a given material, so this conductivity and resistivity, or conductance and resistance, they both are exist in the same material, and these two will be inversely related. Resistivity and conductivity, and resistance and conductance. So finally I can say that resistance, from resistance we can define the reciprocal of resistance as conductance, as G, and from resistivity we can define the reciprocal of resistivity called conductivity. So these are the very basic to understand the current electricity, and very important units are the very important. So whenever you are learning certain new as a definition, try to get its units, and moreover that it's dimensional formulas. Nowadays we forgot about everything about the dimensional formulas, but the dimensional formulas for this conductance resistance, those are also important. So for the next concept, since we derived the Ohm's law gives the V is equal to IR. Now here I would like to derive vector form of Ohm's law. Vector form of Ohm's law. So what it is, how it looks like, vector form of Ohm's law. So what is the necessary to derive the vector form of Ohm's law here? So before that, if you can see the above the given expression V equal to IR. So this is a scalar relation. V is the potential difference. It's a value, it's a number. Current is a scalar. And the resistance is also a value, it's a number. So this is a scalar relation. From the scalar relation to, I would like to relate same in terms of the vector relation. So to relate the vector relation, first I need to relate the potential V to a vector. If you remember the potential and electric field in relation, potential V equal to ED. Suppose if the electric field is exist, so the potential at a point in this electric field due to this location, so potential V equal to ED. So this is the very basic relation what we get from the potential difference versus electric field. Why? Because here the electric field is a vector, so that is easy to take it out to. Now, if we can take that as a basic equation to derive vector form of Ohm's law, if we can write, if E is the magnitude of electric field in a conductor of length L, then the potential difference, across its ends, the potential difference across its ends, we can write that potential V is equal to ED. This is the formula, but here I have taken length as L, because to calculate the resistance we need to depend upon that. So if I take this as first equation, but I know that from Ohm's law, V equal to IR. So this is the second equation. Before writing the second equation, I would like to manipulate these equations like that. So how we can able to manipulate that? Potential V is equal to IR. So we can replace the R, potential V equal to I times, since R equal to rho times L upon A. So I can replace that rho times L upon A. Now let me take this as the second equation. Now if we compare 1 and 2 by comparing, so E times L equal to I times rho times L upon A. Now cut the like terms, L gets cancelled. So write the leftover terms. If you can write that leftover terms, E equal to I times I upon A times rho. So here we define one more definition in terms of I upon A. So this, if you can write that separately, I by A. So this I can write I upon A. Current per area. So current upon area. So this we define as J, which also known as current density. Current density. So the current density we define easily. The current per unit area is defined as current density, and that current density is a vector quantity J, because area is a vector. Length and area, they are the vectors. So the current density is a vector. Now finally I can replace that in terms of I upon A. Therefore electric field E equal to J times rho. So electric field is a vector and current density J is also a vector. So J times rho. Now if you want to replace further, it's not supposed to be dot product, just times. Otherwise, if we will think that as a dot product. Or if you can replace further, since since rho equal to 1 by sigma, since rho equal to 1 by sigma, therefore electric field E equal to J times current density times 1 by sigma, or J equal to current density J equal to sigma times electric field. So here sigma is nothing but conductivity. I will write all the characters at here, and these two formulas are very important. So these two are the relation vector form of Ohm's law. So in the vector form of Ohm's law, we can write electric field E bar equal to J times current density times rho. J times rho. So this is electric field, this is current density, this is rho, resistivity rho. So which gives the relation between electric field, current density and resistivity. So which is also known as vector form of Ohm's law. Or if we can do a further simplification, in the place of rho, if we can write sigma, so we can write that J current density equal to sigma is nothing but conductivity times electric field. So these all are the basic terminology to understand the current electricity. So today's class I introduced to you new concepts, that is, one is conductivity. Conductivity is sigma. So sigma is equal to the reciprocal of resistivity. And after I introduce conductance. Conductance capital G equal to the reciprocal of resistance. And after I introduce current density. Current density J current density J equal to current per unit area. So we can write that as current density J equal to current per unit area. So current we can write that charge upon time, for the simplification upon area. So if you can write that in terms of J equal to Q by T times A. So Q by T, we can write that I. Now current density equal to J. Now finally vector form of Ohm's law. Vector form of Ohm's law. The electric field E bar equal to rho times J bar. This is the relation between electric field rho and current density, or current density J equal to sigma times E bar. So these two gives the vector form of Ohm's law. The relation between electric field and current density sigma and rho.